Righty. So we put out a call for short talk suggestions, vaguely targeting early career researchers. And we got 6 talks, all of which are totally by early career researchers, which I propose to fit into the next 45 minutes by being an isolation kernel so lightweight that it needs no verification. I will do scheduling, and they can introduce themselves, and then there will be, hard real-time scheduling at the 5-minute point.
We're just ticking. Hi, my name is Cebeci, and I'm a PhD student at EPFL. I spent the first half of my PhD building SMT-based tooling, and I want to spend the second half of my PhD trying to systematically ensure that solvers don't blow up. This talk is about our SOSP paper, which will be published in a month, but it's available online to read today. Our thesis is that many system components written in C can be verified as is and with minimal effort. We achieve this through a spec language that is an extension of C itself with a handful of verification primitives that are carefully designed to be expressive enough to specify systems code, but restricted enough to facilitate automated reasoning. And we realize this approach by building a verifier we call Teapot, which is open source and freely available. Teapot makes a set of unconventional trade-offs that are practical in the context of verifying system components. We support low-level C idioms using an untyped byte-level memory model. We minimize annotation overhead, mainly by making verification less modular. And we support specifications written in a C-based syntax, similar to that of conventional test cases. And in exchange, we give up interactive response times. We move verification to a CI workflow, where the verifiers love to run up to an hour. And we also offer a restricted specification language that is expressive enough to specify systems code, but it's far from being general purpose. And we limit our scope to verifying system components. We do not scale to the verification of larger full-scale systems. Now let me show you what these trade-offs look like in practice. Imagine we're trying to verify a system that manages 2 simple counters, A and B. The system has an initializer that allocates the counters and sets them to 0, and 2 API functions, transfer and getSum. Increment and decrement are internal functions that are used by transfer. And our objective is to prove that getSum will return 0 in all reachable system states. We'll first look at what this will look like with a typical interactive verifier that is hypothetical, and then we'll see how Teapot simplifies the process by demodularizing it. With the interactive verifier, we would write our objective down as a postcondition on getSum, and now we would specify the expected system state as a precondition, using some form of separation logic to specify ownership of the pointers. And we would also say that getSum preserves these conditions, that init establishes them, and transfer also preserves them. We would need to write specifications for increment and decrement as well, since their actual bodies are opaque to the verification of transfer. So in total, we wrote 22 lines to verify a property we could agree on in less than a minute. Let's see how we can do a little bit better with Teapot. First, notice that the conditions describing the well-formedness of reachable states are repeated many times. So in Teapot, we write them out explicitly as a global invariant. This makes the specification more concise, but a little bit less modular, because we introduce the full global invariant in the verification context of all API functions, but parts of the invariant might be irrelevant to some of the functions. And instead of writing specs for internal functions, we inline them at all call sites. The trade-off here is that the verification context for the internal functions will now potentially contain irrelevant details, which could slow down their verification. And we similarly remove framing conditions and make the entire heap visible to all of the functions. And replace separation logic with what we call naming logic, which simplifies heap reasoning in the absence of recursive predicates. And lastly, in order to present a familiar language, we take what remains of the spec and express it in C as a test case that should pass in all reachable system states, and a Boolean function that describes the global invariant. One problem with demodularization is the increased risk of solver explosion. The SMT solver is essentially navigating a search space of potential proofs, and irrelevant facts in the search space might plant traps, which could make the solver diverge or take impractically long. Teapot avoids common causes of solver explosion using a tailored spec language, which comes with a careful SMT encoding. We, for instance, provide primitives to quantify our memory regions, but not directly over all values of a type. And we forgo the use of recursive predicates. And instead, we show that many data structures appearing in a systems code can be specified iteratively instead of recursively. To evaluate TPOT, we verified 5 system components that have been previously verified with the same functional correctness guarantees as prior tools. And we observed that using TPOT consistently reduced the annotation overhead by up to a little over 3x, while also the specs being in C. And lastly, the verification time was under an hour for all of our evaluation targets, which shows that TPOT is, in terms of runtime, compatible with the CI workflow. TPOT is open source and freely available, and our SOSP paper is accessible online. And thank you for your attention. I believe Sasha has a question.
Can you compare, do you have a comparison with CBMC? I'm not sure I understand how you bring something, you bring separation logic somehow, but I do not clearly understand how.
So we don't use the full form of separation logic. We have some simplification over it that we think is easier to interpret, but more so, like, it is effective when you don't have recursive predicates. And we don't compare with CBMC, but we compare with CN, for instance, briefly.
Yes, but CBMC would have code specification and the same kind of properties. You wouldn't have to write specifications, and you would run in CI and do unboundable logic.
I don't think we have time, but let's discuss after the session.
One instantaneous question. Okay, thanks.
Thank you.
All right, so my name is Dustin Hoffman, and so I'm here to present a verification language called Resolve and some tooling that goes with it. So Resolve is an imperative value semantic object-based language that's designed around trying to solve push-button verification. So this language is very high level compared to everything else that's been seen this week, and it also suffers from the thing that was mentioned Monday about not doing a great job of growing a community, but it's used at Ohio State, Clemson, Rose-Hulman, and maybe Cleveland State for education. So the reason I'm presenting is so maybe you guys can steal some ideas or get inspired, not to actually expect you to actually go ahead and use it. So the language includes the ability to specify components, but it doesn't include any built-in components. So to add integers, for example, which most languages include by default, we have to go in and we have to go in and define them using a specification. So here's how you introduce a programming type. So the programming type integer is going to be modeled by integer model. So one thing that's key within both the classes as well as how we want people to think about it, when they see a variable, they need to think about its abstract model. And so this is the... I can't remember how to do that on Mac. Shoot, you just killed me. Control plus? There we go, sorry about that. All right.
Because now the colors are black.
I can't understand, what'd you say?
Unselected.
Okay. All right, so it's modeled by integer model, which we see up here as a subtype of integers, and it's restricted within a min and max. So we look at the specification for increment here. This procedure is for a kernel, which is the basic minimal set of operations we'd think you would need. And so here you can see we have a variable I coming in, which is a type integer. And then we have this updates in front of it. Updates is one of the parameter modes. So there's like 4 parameter modes in Resolve. An update says we care about the incoming value, the outgoing value is going to be changed according to the insurance clause. So these can be short-term notations for how variables changed. We'll see a few others later. It has a normal requires clause ensuring that it's going to be less than the max. And then we do an ensures where we say the outgoing value of I is equal to the incoming value of I plus 1. So here the notation, the pound I tells us that the abstract value of, or pound I is the incoming value for I. And when you reason about this, it's on the abstract value, not the implementation of integer. So moving forward, if we have a layered operation here for add, and again, this shouldn't be too surprising. What's going on here, we have an I and a J. Here we have restores as a parameter mode. So this tells us that the incoming and the outgoing value of J are going to be the same, but during the actual implementation, they may change. And then one thing to notice here, when we talk about the outgoing value of I is equal to the incoming plus J, and then J doesn't need the pound because the incoming and the outgoing value are the same. So you could put the pound there if you wanted. Moving forward, this is an implementation. It's an iterative loop. and we can actually verify this. So this would go off to a decision procedure that was made through the math department at Ohio State. And here we're able to actually verify it. We can actually allow the users to see what was being proved at each step. And so this associates back with program line. You can switch it over to a state as well. But we found that it was easier to see that way. And then if you were to break it by commenting out a random line, we verify it again. As you would expect, it fails. And then it'll tell you what proofs it couldn't find. And the idea is that the user can go back and find where things were out, which lines things were off at, and reason about how to fix them. So quickly about the tooling, the kind of environment you see is kind of long in the tooth now. This was before Visual Studio Code. So this was a web-based thing built about 10 years ago. But it allows you to chain together verification tools. It's not designed just around Resolve. So we do things where we verify Java and other languages in it. You can also combine multiple provers. So we have like Z3, and then I also mentioned this split decision, which is our decision procedure built in as well, and allows you to have multiple configurations of these. And that's why you would select from up here. So it was a whole tool chain around it as well. So it's an interesting design. It's a historical anomaly, but maybe you'll find some use to steal from it. That's all. Any questions?
Questions?
Survey to execute code?
Not on the version that I have. The Clemson University had some work on compilers. Ohio State refused compilers for some reason. I didn't totally understand my advisor's stance around that. But Clemson does have versions of it that can be compiled and executable. Warren, did you have a question?
Oh, yeah, I was just wondering, how do you get content in? I mean,
Oh, so there are models of those, and then so at that kernel level, when you actually had a compilable version, you would have to provide more manually implement or verify things that actually would tie it to the operating system. So it focuses more on the high level, but when you do have, and there are specifications for input-output operations, but the actual final implementations of those, we're going to have to go back to another language that maps over, and then that would be a more manual verification.
So there's some translator that gets content.
I mean, I want to investigate something that's written in some language like C. I just want to know how to get it all in there.
You mean like input-output from?
Yeah, I mean, I've got a big C program. I want to
Specify a property about it.
So we do have input-output designed around a string theory that also
Warren is asking whether you can translate some program into it.
No, I'm not built a translator into it.
Okay, thank you.
Okay, thank you.
Thank you, Peter. Hello, everyone. Hi, folks, and thank you for organizing this amazing workshop. So, I'd like to talk about a work we've been doing for quite a few years. In particular, is the Flash. And this idea, by the way, that was suggested by Andrei Morhov, is to try to mix a compiler and a build system for something I call a hybrid document, which is something like a document that can contain very different, is a literate, but also we allow to contain different kind of codes like Groq or C code or many things. And yeah, and Flash is basically a build system, and in particular, a short presentation is basically you have a check. So you update a document, you can update a document, version a document, I have a new proof document, and then you can check it incrementally, and you have this document type that then you can consume. And well, there's a lot of details, but it's basically a build system for documents, and you can implement a lot of stuff on top. We have implemented like an LSP server, a reinforcement learning agent. There is people implementing like Copilot, Butterproof is for mathematics, GSCOG, for example, we have a new version. And in particular, so we have like an implementation right now for Groq. There is some toy implementations too for other languages like in the Camel, other theorem provers in the Camel family. And also we have the implementation, which is this part. There is a comprehensive one. Goal too is to have a theoretical model is under development. And then the internals, this is the externals, like it just very says you say, just build my document until some point or until the end. And then the implementation is defined as an interpreter stack and some algebraic effects. And yeah, and right now, I think the best test is we have a huge, we load like thousands of code files, and we do like operations on that, like learning or changing, and we can do that in 20 gigabytes with very good properties, respecting like what will be like a non-interactive setting. And yeah, why we did this is to try to understand better what a document is. And this is coming from the work on mathematical components library. If you have seen George Contier presentations, he always relates mathematical tests with the code version. So I'm very interested into trying to improve that. And yeah, no, actually, I think it's clear in the words of like, we have a super heterogeneous land. So this is an attempt to understand better this heterogeneous document that can have a lot of different components. In this case, we have Groq or C code, but and also to have a little bit of principle design. There is not a lot of people, of course, in all these tools, you need interfaces. And while there is a lot of papers that describe what these interfaces do, there is not so many that explain the internal details. So this is what we are trying, right? Like, and yeah, and well, I guess here is all of you are very familiar with how painful tooling can be. So you could also interpret why we did this is to try to make tooling less painful. And well, for now, I think it's working. More rigorous. There is a paper that is still being redone with some evaluations, and I think the results in this sense are also positive. And well, and to conclude, I'll do a very quick demo, but to conclude is where would you like to look at Flash? And I think right now, if you're a Groq user, you should try. It will have different trade-offs to what you are used to, but maybe it will improve what you can do. And if you are educators, you have, for example, you can try it out. It's fully deployed. This is all internet on github.dev. Unfortunately, there is some little bugs. In particular, it's very slow. It downloads a lot of 200 megabytes because some bugs in compression. This will be fixed soon. So I see 3 people could be interested. It's educators using Groq right now. Implementers could take ideas, even implementers could code. If you tool is in a camel, or you could take ideas for design. And in particular, researchers, we have some success. So for example, now machine learning is the thing. So it's quite optimized for machine learning, this petanque system. Right now, and working pretty well. As I say, for example, this last one was like 2 weeks running and didn't crash or anything, so pretty convenient. In software engineering, for example, I think many people want to experiment with documents or code proofs, etc. That's very interesting. And in HTI, I think that also this is working quite well. And yeah, for example, this is a paper just affected today. For example, using this petanque server. And well, very quickly, so this is, for example, Groq LSP. So as you will expect, it's an interface. You see, you can go to code. I don't actually know why there is an error here. I don't know what is decided to fail. Okay, well, demo failed. But for example, this is something a bit more interesting. And it's Groq is but Groq and Markdown document. So you see, for example, we can do the preview, but still, yeah, I don't know why the other file was failing. But still, you can see, I can interact, you see. I have the preview here. I can move it to here. And yeah, and maybe I'll roll one last example. Yeah, no, I have 5 minutes right now, yeah. But this is, for example, this is like JSON code, goes inside. Yeah.
Thank you.
And you can interact with it. Thank you. Yeah, and my
Question?
sorry.
Could you say something very briefly about how you're using algebraic effects? I didn't get that bit.
Yeah. So we are using them because the idea is that all the interaction. The idea is like if there is no interaction, this corresponds to the linear compiler. So the idea, so this is like a reference. So the idea is like if there is no interaction with the document or errors or stuff like this, there is no effects, and all these things you get in interactive use are modeled through effects, and then give us quite good ergonomics of implementation-wise. But yeah, it's hard to measure formally what the advantages are, but yeah.
Thank you.
Okay, thank you.
Hello, my name is Hans-Dieter Hiep, and I'll try to summarize my thesis in 5 minutes. My thesis is called New Foundations for Separation Logic. I worked on it at Leiden University and at the CWI in Amsterdam. So, New Foundations for Separation Logic. On the left hand, we had the foundations for program logic as that is now known for more than 50 years. We have first order logic at the top level, then we have horse logic at the middle level, and we have dynamic logic at the lowest level. First order logic has a nice property proven by Gödel, which is Gödel's completeness theorem. Then horse logic has this nice property proven by Cook, which is relative completeness. And then dynamic logic increases the expressivity because you can nest the program modality representing the weakest precondition axiomatization. On the right-hand side, we now have how it looks like for separation logic, but I first want to do an alias analysis. Because in the literature, separation logic is used for both the first layer and for the second layer, but let's separate this out. And actually it was David Naumann who did this in some unpublished note a long time ago by calling this second layer Reynolds logic. So we can now talk about separation logic, the logic on the top level, and Reynolds logic at the middle level. So just like horse logic has relative completeness, so does Reynolds logic also have relative completeness, which is very nice. But if you look at separation logic, what about completeness of separation logic? Well, it turns out that the standard interpretation for separation logic is incomplete due to incompactness, but I won't go into the details in these 5 minutes. Below we have something that I introduced in my thesis, which is called dynamic separation logic, by adding the weakest precondition as a modality to separation logic. And it turns out that there are now 2 alternative axiomatizations of this modality. The one on the top is the weakest precondition as was given by Reynolds. Let's call this the implicit alias analysis. And the one below is an alternative way, but it is also a weakest precondition. Let's call this an explicit alias analysis. And the problem with explicit alias analysis is that this blows up. And this is the whole motivation, the scalability argument behind separation logic. You don't want formulas to blow up. However, because both are weakest preconditions, you do expect them to be equivalent. And semantically, this indeed holds. However, can you also prove that this equivalence holds? Well, to do that, let's introduce a new connective, which I call the at connective. And it is a connective in which you can reinterpret the meaning of the points to predicate on the left-hand side. And the right-hand side is a description of the heap with respect to which the left-hand side is interpreted. And the beauty of this at connective is that it helps you with axiomatizing how the points to predicate and the separating connectives interact. So my claim that is in my thesis is that this connective can be used to indeed show a proof system which is complete with respect to not the standard interpretation, but the interpretation of separation logic with respect to the first order definable heaps. However, more stuff is coming out of this. There is also a relative completeness result for separation logic. But I don't have the time to get into that. So, yes, if you have time and interest, please read my thesis. However, I also post sort of more accessible blog posts on my website. And yeah, the reason I chose this and not my own last name is because it has the same pronunciation. So this is actually... Okay, thanks.
Extra question time.
This may be sort of, but I got excited when he said new foundations. Is there a connection to Quine's new foundations for set theory? Nice phrase.
Yes, there is a connection. Quine's new foundation is reducing set theory to essentially 2 axioms, or axiom and axiom scheme. It's all about comprehension. And if you read my thesis, it's all about comprehension in separation logic. But there is also a connection to new foundations for logic by Karl Popper. Because there is a methodological argument behind logic. You should not have an ontological import. So that's also in the thesis, in case you're interested. Yes. Thanks. Thanks.
What is relative completeness?
Relative completeness is that you have an expressivity assumption and an oracle. It basically assumes reduces to verification condition generation. And then you throw those verification conditions to an oracle that can solve them for you. Typically this is some SMT system, or sometimes if it cannot be done automatically, you have a human that does this. And so it is all relative up to this expressivity condition and the oracle. So this is a classical result by Cook.
Good afternoon. I'm an early stage researcher at a company called Groq. And we don't do much yet about big spec, but we're getting there. So we're going to tell you about a few things that we do. But let me first tell you what our company does. Our company makes silicon chips for running machine learning models. So if you go to our website, groq.com, you get a chatbot, you can ask a question. I've asked it to write me batches Bytonic merger algorithm in Haskell. It did it at 1,200 tokens per second, and it did it instantly. So that's what's kind of interesting about this. And this runs in like about 600 chips, all working together to give this answer. So I work on the design of these chips, the compilers for these chips, and their verification. So what happened? What happened there? So we make silicon chips. That's our business. And our chips are very weird. They don't look like processors. They don't look like GPUs. They're based on these matrix multiply engines which work in parallel, and that's what's the basic operation of most machine learning algorithms. And we have this kind of systolic architecture and disaggregated computer memory. So it's like a very different chip, but that's not the subject of this of this talk. And you know, as now that I'm a machine learning person, I thought maybe I'll grow up to be like a mathematician. But I've just discovered in the last couple of days I'm probably a physicist or a chemist. And if you were to take the lid off one of these chips, you'll see this kind of lane-orientated computing with computations moving in lockstep at a cycle at a time. And you know, if you were to look at one of these lanes, it has matrix multipliers on it, a vector engine, some memories. But what I'm going to talk about in this talk is something called the SXM. So that's like a switch network which lets you move data from one lane to another. And there is an instruction set, and we've got seal-like ambitions to come up with a nice spec for this, which we can link the compiler and the hardware. But that's a different talk. So we take these chips, we put them into nodes, into racks, and we run giant, large language models. So one of the jobs I had to do was to formally verify a switch network called a Benes switch network. And you can find out about that by going to the Wikipedia page for Clos network. If you go to the bottom, you'll see this little wee switch network. And its purpose is to take some input bits, and then you can then navigate any one input bit to any output bit. And it's got a nice kind of recursive structure. So that's my spec, this picture. And my job was to make sure that the engineers who had implemented the hardware for this did it correctly. So what did I do? Well, I thought, well, if my spec's a picture, I should find a way of trying to draw it. So I came up with a way of doing it. I have to warn you, earlier in this week, we were told not to do two things, and I didn't get the memo, and I did both of the things I'm not meant to do. I used Haskell as a DSL, and I used dependent types. It's too late, and it's already been done. So I made a wee library in Haskell to let me draw that picture. And I used my normal Haskell tricks, making higher order combinators which have got recursive divide and conquer strategy. Here's one called interleave. Takes a big problem R, decomposes into two smaller problems R, and solves the sub-problems and produces the answer of some kind of odd even decomposition. And the main reason I call this library haste, and I mainly use it to program the chip. So you write computations, and you get, this is MLIR, which so Tobias showed you earlier on, and this gets compiled and runs in code. But the same library can also generate hardware. So this Benes network switch you saw at the top, I can use the same combinators like interleave and so on, and these will generate hardware. And this is like a dependently typed description of how you would do that in Haskell. And so then I can come up with a description, draws a picture, I look at the picture, make sure it's the same as the spec, and then I have an alternative interpretation that produces hardware from that picture that acts as a golden spec. And then I run I run tools. I run formal tools which make sure that they're equivalent. It takes a second. Me actually worked out. I'm running out of time. I mean, that's another. And then we write properties using LTL logic, and we run the model checker, all the usual kind of stuff for hardware verification. So that's what we do. The only fly in the ointment is if you go to the Wikipedia page for Clos Network and you look at a description of what Clos Network is, notice how that picture looks quite similar to the one that I drew. Well, that actually is produced by my Haskell DSL program, and it's actually my own picture. So maybe I do have a secure foundation for this verification. That's it. That's all to say.
Was that a question? Or was that not?
Yeah, no, it just looked like your two networks in the center where you just switched them, they were back to back, the same thing. So was that a NOAA?
Let's talk about it later on, because as long as details are not there.
Okay.
Because there's that control inputs in there, which could tell you whether each thing does a swap or not.
So maybe you were too fast for me. What is missing? So you have description, you generate what you want, you verify what you want. What is missing?
No, nothing special about it. It's very cool. I verified the silicon design. I think that I got taped out, and I know it has no bugs in it.
Is that a question here? Is that conventional industry model checking, or your very own?
No, Yosys HQ, we can't afford Jasper Gold, so we use the Yosys HQ tools that are based on Verilator, Z3, CBC4, etc. So that's the stack. And we use the quality checker, and then we'll use the model checker for when we wanted to do K-induction, etc.
All right, thank you very much. So this week we heard a lot about big specification.
You have to introduce yourself.
Oh yes, this is a good point. I'm Xavier. I'm currently a postdoc in Peter Muller's group at ETH Zurich. This is going to be a really short talk, probably less than 5 minutes. I just want to ask for your help. And so first, let me tell you what I want your help with. So we heard a lot about big specification this week. I'm going to talk very, very quickly about something related but different, which is big verification. You know, we've all seen variants of this graph. Like everybody, I'm sure everybody here has written some version of this, verification curve. Like, oh, you have to put in a lot of effort, and eventually you get a payoff, right? And we all want it to look something more like this, right? And so the problem is we have this area in between, and this is where all the research is done, right? Like, oh, I have some idea. Like, I could write a specification language that's a little bit different, and I can carve out a little niche, or I can build a better SMT solver and whatever. And this is, of course, based on our intuitions as researchers. What we're interested in is trying to figure out, sort of more empirically, what are the common problems shared by all the wonderful tools made by people in this room? What are the experiences of the users of those tools, so that we can hopefully provide better grounding for the development of future verification tools, right? So what do I want your help with? If you verified, real software, if with your tools you verified real software, or you know people who verified real software, we very much would like to talk to you. We're doing a study where we're doing 1-hour interviews with people who've used verification tools at scale. It's all over Zoom, so we can accommodate you wherever you are in the world, whatever time zone you're in. And of course, all of our data is kept confidential. And in the end, we hope to publish a paper resuming the interesting findings that we find in all this and share it back with the whole community. So that's all. Thank you very much. Robert.
What is the definition of real software?
It's subjective, but I don't know. I guess intuitively, I would say software that actually runs and is maybe above 500 lines of code.
But so suppose you have verified, let's say, a type system of some programming language. Would you consider that to be real software? Or?
We're really looking more for, I guess, I should have said instead of software, programs. Like we're looking for something that is executable, right? So something that, so if you verified a type checker, I think this is much more in our problem space. Yeah. Yes.
Is this the same interview thing that was shared on the Lean Zürich?
I don't know. So unless somebody shared our interview there, I at least didn't do that. So yeah. Yes.
If you participate, what do you get? Do you get a, like a ATH cup or something, or what?
I think I might have stickers somewhere.
I'm not sure if stickers are going to do it.
Well, we can see. We'll see if we can come to an arrangement.
So
Funding and organising verification surveys is a big topic for this workshop.
Oh, I see. Okay, so, well,
Maybe-
when I hear something like this, I mean, I can think of 50 things or 100 things if I could spend hours to write them all down, but they're all in the ACL2 log. There are hundreds of places where we hit the wall for some reason or another and something had to be fixed. And this goes on all the time.
Yeah.
And so anytime anybody builds a big system, they hit the wall doing something. So all you need to do is find people that build big tools.
Yeah, well, it sounds like we should talk to you.
But not for a sticker.
Okay. Well, I'll see. I mean, I'm supposed to go to Texas soon anyway, so I can bring a coffee cup. Yes.
No, it's got to be an ETH cup.
Yeah. I mean, an ETH one. Yes. Sorry.
If you build a real verification tool which itself is verified, is
That-
that real software?
Yeah, that definitely sounds like real software.
Is Iris real software? Is F-star real software?
This is why I said it's a subjective criterion, right? I mean, we're really looking for people who are pushing the limits of verification tools and trying to figure out, what are the blockers towards wider spread adoption of verification tools.
Are you, I guess the answer is you want both, but are you distinguishing between users of verification tools who are also their authors and the other kind?
We do want both. We accept both, and yes, I think in our results we'll most likely have to partition the groups into to separate their insights, basically. Yes. I should also mention this QR code contains a lot more information on the study, along with a sign-up link where you can book a slot if you're interested. Yes.
Could you just draw that on a blackboard?
Given some time, probably not in the 2 seconds that are left to me.
I think he was talking about maybe an HTTP address.
Oh, yes, that I could. I can definitely do that, yes.
Yeah, I meant the QR code. Final question. Final question? I think probably everyone's tired. Thank you. Everyone.